Hello everyone, I am Arpit and our group is here to present you the paper presentation about the relationship between trust in AI and trustworthy machine learning technologies. Let's have a look at the outline of our presentation. Here we are going to present you the topics. First, introduction, the concept of trust, trust in principle for social sciences, basics of machine learning, then machine learning principle and chain of trust, benefits, trust in AI based system, and at last FISH technologies and conclusion of our paper. Now let's begin with the introduction first. We all know that growing interest in the ethical aspect of artificial intelligence and machine learning has generated a focus on how to ensure that present and future practices are trustworthy. The current emphasis on this area reflects recognition that maintaining trust in artificial intelligence may be critical for ensuring acceptance and successful adoption of AI-driven services and products. And additionally, perception of trustworthiness, impact on artificial intelligence, and accordingly influence a person's decision and behavior associated with the service or product. So, in this paper, author described the connection between trust and machine learning technologies in a systematic manner. Well, the aim is to identify how technologies impact and relate to trust, and specifically identify trust supporting machine learning technologies. It is important to highlight the difference between studying trust in AI and studying ethics of AI. So, trustworthy AI is related to regulating statement on the qualities of the technologies and typically requires ethical approaches, while trust is a response to the technologies developed or processed through which they were developed. And also, this paper is about identify the ways in which machine learning technologies might enhance or impact trust based on trust framework drawn from the ethics, social sciences, and computing and algorithm design literature on the technological trust qualities. So, in this paper, author introduced FISH classification of machine learning technologies, that also called fairness, explainability, auditability, and safety, and that support and allow trust and establish the relationship between this trust enhancing technologies and HET. It is also called human, environmental, and technological qualities. Now let's moving on to the concept of trust. As you might know, everyone has their own personal interpretation of trust. For example, in the specific case of machine learning, cybersecurity experts mostly consider security and privacy preserving aspect as being trustworthy. Activists normally use being ethical or consider being ethical as trustworthy, and machine learning experts focused on accuracy and efficiency of the algorithm. Even in the wording of the trustworthy machine learning is ethical machine learning and trustworthy machine learning are somehow used interchangeably. But when it comes to the principle in social sciences, the way people trust is actually based on the three modern definitions called benevolence, integrity, and ability, or a framework that is abbreviation of all these things that is called ABI. And if you add the predictability over time, that's the plus, which is more modern framework. And each aspect of a technology, or in case of machine learning system, should reflect these principles. The focus on this paper is only on the technological things or technological solutions that are in align with this definition of trust for trustworthiness. This model discusses the relationship between a truster, which means the entity that trust, and a trustee, which means the entity to be trusted. In the ABI model, ability is defined as the perception of that group of skills, competencies, and characteristics that allow a party to have an influence within some specific domain. The specific domain is crucial as assessment of a party's ability will vary according to particular task or context. Benevolence is defined as the extent to which a trustee is believed to want to do good to the truster. And to be considered to possess integrity, a trustee must be perceived to follow a set of principles that the truster find acceptable. And this requires confidence that the trustee will act in accordance to a set of principles and that those align with the value of the truster. ABI's framework has been adapted and expanded to acknowledge the importance of predictability or reliability in shaping perceived trustworthiness, while ABI plus model suggesting that the four key characteristics on which judgment of trustworthiness are based, which is ability, benevolence, integrity, and predictability. When talking about predictability, it will reinforce perception of the ability, benevolence, and integrity of the trustee. So, considering the role of predictability, it draws attention to the importance of trust being sustained over time through ongoing relationships. As well as being saved by judgment of trustworthiness, the act of trusting also depend on a range of external and conceptual factors, personal attributes, and behavior of truster. So, as the context changes, for example, relating to cultural, economic, political, or personal development, so level of trust and perception of trustworthiness also change. Therefore, trust is characterized as an ongoing relationship rather than a static concept. Furthermore, the authors recognize three types of condition to demonstrate the potential for a technology to be perceived as trustworthy, which is human, environmental, and technological qualities. So now let's talk about human qualities. Well, it refers to the action that attract individuals having a risk-taking attitude. The effectiveness of this quality depends on the personality type, past experiences, and cultural background of the individuals. And this is a link to the ability of the trustee to satisfy the curiosity of the truster in testing a desired task. Moving to environmental qualities, it considers elements that are enforced by the qualities of the technology provider. First, it heavily relies on the nature of the task that the technology handles, and the complexity of the task has a potential to attract trustworthiness or cause distraction. The pattern of the establishment of trustworthiness differs in various places depending on the education system, level of their accessibility to novel modern environment, and various fundamental cultural backgrounds. Finally, technological qualities determine the capacity of the technology itself to deliver the outcome as promised. This commitment is multidimensional, and the technology needs to generate the result efficiently. Therefore, it needs to establish an agreed performance metric and assure it outcome produces into a desirable range of metrics. Second, the technology should define concrete boundaries for the solution. And for this, the user of the technology should be provided with enough information to understand the purpose of the technology and set their expectations sensibly based on such understanding. This aspect outlines the relationship between performance and purpose aspects.
Hello everyone. Next part of the paper reviews the basics of machine learning, the notion of machine learning pipeline and related chain of trust. Machine learning is a part of artificial intelligence that makes predictions from data by using algorithms and statistical models. A machine learning algorithm is basically a function as y equal to fx. In this equation, f represents the function that maps input to the output or the machine learning model. The input of a model X corresponds to a set of features which is a vector of values that represents data or dataset. Finally, Y represents the output of the algorithm to fulfill the task that is meant to undergo supervised, unsupervised, and reinforcement learning. In supervised learning, the output Y is meant to be an assignment of the input X to a predefined label set and is used in object recognition, machine translation, and filtering spams. For example, a fraud detection classifier would assign two labels, fraud or benign, to an input feature that is derived from a transaction. Unsupervised learning methods are used when the input X and output Y are both unlabeled. In these methods, the task is to determine a function f that takes X as input and detects a hidden pattern presentation as output Y. Reinforcement learning methods map X to a set of policies as Y. In these techniques, the function f determines an action, an observation, or a reward y that should be taken into account when situation x is observed. The use of any machine learning algorithm implies activities in various stages, called the machine learning pipeline, as depicted in figure 2 through the chain of circles. First, one collects the data from a source and stores the digital representation in a database called data collection. Then such data undergoes pre-processing methods to extract certain features as X in the machine learning equation, labeled data preparation and feature extraction respectively. When X is ready to be processed for the supposed task, the features are divided into at least two groups to attain two purposes. The first group of features, training, are used to tune and optimize the output Y of function f. The group of features for this purpose is called the training data. The training process can be offline or online depending on how static the training data is with respect to the life cycle of a model. In the testing phase, verification is done by assessing the efficiency of the performance through some chosen metric. For example, in classification, a typical accuracy metric is the proportion of the test data that has been mapped to their original label correctly by the function f. When the model passes the verification stage with a sufficiently good performance, then they are applied in the wild. This stage is known as inference, in which the trained model is deployed to face unseen data. In this context, y is computed for fx when x is unknown, that is not contained in either test and training datasets. So, the first group of stages concerns data-centric aspects involving data collection methods, pre-processing techniques, and extraction of useful features for the analysis. The second group of stages is model-centric, the stages in figure 2 that deal with the tuning the model to the best performance, that is training stage, evaluating the trained model for confirmation of the desirable performance in the testing stage, and deployment of the model for the real-world application in the inference stage. Based on the machine learning pipeline, it becomes clear that technologies may impact trust in the resulting service or product in various stages of the pipeline. In this stage, stages may impact on each other in terms of level of trust they are able to propagate. It was noted that where trust is established or damaged based on visible outcomes at later stages, the resulting levels of trust will have implications for trust in all stages of the development of future technologies. The second dimension present in the chain of trust results from the fact that a service or product may iterate through the stages during its life cycle, possibly multiple times. This occurs, for instance, when new data is being introduced to improve the training, and through this, the inference. A third dimension with the notion of chain of trust is the development of trust through the stages of design, development, and deployment of AI-based service or product. A final dimension to consider in this context of chain of trust is that of accidents, sudden breakdowns of trust, or failures, such as in case of security breaches. Finally, the chain of trust provides guidance for experts and the public how and when to evaluate the trustworthiness of the system in relation to the principled framework, not only in the final outcome of the system, but also in all the inner stages that lead to such outcome. The next section aims to establish the connection between trust in AI-based solutions and the trustworthiness of the underlying technologies, and further divide the discussion in data-related concerns with a focus on data collection, data pre-processing, and feature selection, and the model-related concerns with a focus on the stages of model training, testing, and inference. Data collection involves reading data from various sources reliably, for example, sensors to collect environmental data, a smart speaker listening to audio commands, secure transmission of the data from the collection point to a machine for the purpose of storage, or online analysis, storing data in the server. One of the main trust concerns in data is in protection against privacy violations and other forms of illegitimate use of one's data. Model-related trust concerns trust in the working of the models and algorithms. Many of the trust concerns relate to a fear that algorithms may harm society or individuals because they are unfair, without accountability, and non-transparent. The question is what the role of technologies in dealing with the model-related trust concerns. At their core, machine learning models and algorithms are optimized for accuracy of results and efficiency in obtaining these. While the accuracy and speed of results might be considered to demonstrate basic functionality or ability in, they do not necessarily satisfy or align with other trust qualities. The trust concerns discussed in the previous section are related to concerns that have been raised widely about the impact on society of the proliferation of AI, resulting in the emergence of a large number of policy frameworks that relate to principled AI frameworks, that is, policy frameworks to enhance and regulate fairness, accountability, and transparency of particularly AI-based services and products. These principled AI frameworks present varying sets of qualities that AI-based systems should follow to be considered trustworthy. Some principled AI frameworks also apply to technologies other than AI. So there is emerging literature reviewing principled AI frameworks that provide critical analysis of frameworks for ethical machine learning and highlights a number of challenges, some of which require attention, and these frameworks often fail to realize dependencies between policy objects. Example, addressing discrimination issues might lead to unexpected privacy leakages. Current frameworks are focused on privacy, transparency, and fairness issues, but this needs to be shifted toward understanding such tensions and reframing core research questions. The next part will be presented by Preeti. Thank you.
Simran. Hello everyone, my name is Preeti and I will continue the next section of the paper discussion with FEAS. Trusting a technology is not limited to FEAS. There are other factors such as user-friendly UI or presentation with the result of meaningful plots. So, what does the author mean by FEAS? F stands for fairness. The technology is focused on detection or prevention of discrimination and bias in different demographics. E stands for explainability, which means technology is focused on explaining and interpreting the outcome to the stakeholders, including the end users, in a humane manner. A is used for auditing technologies, focused on enabling third party and regulators to supervise, challenge, or monitor the operation of the model. Finally, safety technology stands for technology focused on ensuring the operation of the model as intended in presence of active or passive malicious attacker. Author identifies framework with FEAS technology classes and found that all the frameworks were in the same way related to FEAS. The next few slides explain a little bit on FEAS classes. First class of discussion is fairness. The most difficult part of this class is to understand how to measure unfairness. Author describes three ways of measuring it. The first is by reducing bias within the dataset provided to artificial intelligence. Second is by adding a regulatory term for a logistic regression classifier. And finally, enforce output of the model to generate the fairness notion. Class is explainability technology. Explainability increases trust and can be of two types. First, explainability of an application. And second is explainability to understand the way in which a classifier is coming up with its output, mainly by using intelligible models. There are two main approaches in explainable solution. The first one, known as ex ante, refers to the use of highly intelligible model to obtain the desired prediction. The second one, known as ex post, refers to the use of second model to understand the learned model's behavior. In ex ante approach, an explicit prediction function analyzes features coefficients to understand impact over a decision, decision tree, or a decision list. The ex post approach uses explain. Next class for discussion is auditability. Auditability in machine learning may involve assessing the influence of input data in the output of the model. This ensures predictability, a process that is also referred as decision provenance. Decision provenance have two objectives. It should provide the history of particular data and it should provide a viewpoint on the system's behavior and its interaction with its inner component or outside entities. The final class is safety. The security and privacy foundations of a machine learning model is not different from classical security model of confidentiality, integrity, and availability. But author omits availability because of its general relevance. Careless preparation of the stored data can leak information to attackers, but confidentiality can be enhanced in many ways. For instance, through approaches for different privacy, homomorphic encryption, or cryptographic integration in machine learning algorithms. Integrity can be enhanced by either preventing tampering, such as pre-processing, or by discovering and possibly repairing tampered data. To conclude, this paper established the connection between trust as a notion within social science and the set of technologies that are available for trustworthy machine learning. Paper related the ABI Plus framework and HET technology qualities for trust with categories of machine learning technology that enhances trustworthiness. Four categories of technologies were identified that are fair, explainable, auditable, and safe. This paper gives a close relationship between technologies to improve the trustworthiness of AI-based systems and those that are being pursued in ethical AI and related endeavors. That is all from Group 10. We are open to questions. Thank you.